This is General Chemistry. We continue to learn about stoichiometry, and today we will be looking at chemical reactions. In previous videos, we learned that stoichiometry helps us understand relationships between reactants and products in chemical reaction. For example, in a reaction between sodium chloride and silver nitrate to produce sodium nitrate and silver chloride, if we know the amount of sodium chloride used, we may figure out the amount of other species in this reaction. We also learn about mole and how to relate it to several other quantities, such as the number of atoms or molecules, the mass of atoms or molecules, the volume of gas, and the concentration of solution. We then use the mole concept to understand chemical formulas. Some compounds may have identical empirical and molecular formulas. For example, pyruvate acid, which involved in many metabolic pathways, has the same empirical and molecular formulas, C3H4O3. However, for some compounds, the empirical and molecular formulas are different. For example, ascorbic acid, which is a key chemical component in vitamin C, has the empirical formula of C3H4O3 and the molecular formula of C6H8O6. We also went over how to use percent composition and the mole concept to figure out the empirical formula and the molecular formula of certain compounds and of certain substances. And in this video, we will take another step further and see how stoichiometry can be used to solve certain problems in chemical reaction. Let's say we have a chemical equation A plus 2B forming C plus 3D. When dealing with chemical equations, first we need to make sure that the chemical equation is balanced. Then we can use mole to relate all the species in the reaction A, B, C, and D. To make this a little more clear, let's take a look at an example. In this question, lithium metal reacts with water to produce lithium hydroxide and hydrogen gas. How many grams of lithium metal are needed to produce 5 grams of hydrogen gas? In the first step, we have to make sure that the chemical equation is balanced. On the left-hand side of this chemical equation, we have lithium, hydrogen, and oxygen. And on the right-hand side, we also have lithium, hydrogen, and oxygen. The total number of lithium is 2, hydrogen is 4, and oxygen is 2. And for the right-hand side, lithium is 2, hydrogen is 4, and oxygen is 2. Everything matches. That means this chemical equation is balanced. The next step is to use mole to relate all the species. And the key species they are interested in is lithium metal and hydrogen gas. Since they give us the amount of hydrogen gas, we will convert this to mole. And we know that N, which is mole, is equal to mass divided by molar mass. And that is going to be 5 grams divided by 2 grams per mole. And that is going to be 2.5 mole of hydrogen gas. Now we're going to be looking at lithium metal, and we can see that the mole ratio of lithium and hydrogen gas is 2:1. That means the mole of lithium is going to be 5 mole. And we know that N is equal to mass divided by molar mass. So the mass gonna be equal to mole times molar mass, and that is going to be 5 mole times 6.94 gram per mole, and that is going to be 34.7 grams of lithium, and that is the answer. Now we are going to look at another important concept in chemical reaction and stoichiometry, and some exam love to test you on this, and it is limiting reagent or limiting reactant. This type of situation happens when they give us the exact amount of more than one reactants, and then we have to decide which number or which reactants we're gonna use in the calculation. Limiting reagent or limiting reactant is the reactant that will be completely used up in that reaction. So it is the species that will dictate the reaction, and we will use it in the calculation. Let's say we have a reaction of A plus 2B forming C plus 3D. Limiting reagent here will be either A or B, whichever one that will be used up first in the reaction. In order to deal with this type of questions, first we have to balance chemical equation or make sure that it's already balanced. Then we will determine the limiting reagent, and then we will use more of that limiting reagent to relate all the species or use it in the calculation. To make this a little more clear, let's try a practice question. For this one, under a catalyzed process, acetaldehyde reacts with oxygen gas to yield acetic acid. If the reaction is supplied with 33 grams of acetaldehyde and 16 grams of oxygen gas, how many grams of acetic acid will be produced? Again, the first step is to make sure that the chemical equation is balanced. On the left hand side, we have C, H, and O. And on the right hand side, we also have C, H, and O. The total carbon in the left hand side is 4, hydrogen is 8, and oxygen is 4. And the total carbon on the right hand side is 4, hydrogen is 8, and oxygen is 4. Everything matches, that means this equation is already balanced. The next step is try to determine the limiting reagent. The questions give us 2 reactants and their exact amount, 33 grams of acetaldehyde and 16 grams of oxygen gas. So we have to decide which one is the limiting reagent. First, let's take a look at acetaldehyde, CH3CHO. So they give us the 33 grams of acetaldehyde, and that has to be converted to mole. So we have to divide it by the molar mass, which is going to be, let's say, M gonna be equal to 12 plus 3 for hydrogen plus 12 for carbon plus 1 for another hydrogen plus 16 for oxygen. That's gonna be 44 grams per mole. So we can do that. 44 grams per mole of acetaldehyde. And we can see that 2 of acetaldehyde will give out 2 of acetic acid. So we can multiply it with 2 more of acetic acid divided by 2 more of acetaldehyde. Alright, so that is going to be 33 divided by 44. That is 3, that is 4. This is going to give us 0.75 mole of acetic acid. So if we use up 33 grams of acetaldehyde, it will give out 0.75 mole of acetic acid. Now let's try oxygen gas. For oxygen gas, it gives us 16 grams, and that has to be converted to mole, which is going to be 32 grams per mole. And we can see that 1 oxygen gas will give 2 acetic acid. That means 2 mole of acetic acid per 1 mole of oxygen gas. That's gonna be 2, and that is going to be 1 mole of acetic acid. So if we use up oxygen gas 16 grams, it will give us 1 mole of acetic acid. That means acetaldehyde gonna give lower number of mole, gonna be limiting reagent. And it's gonna be the one that is used up in the reaction. So the species we are going to use in the calculation is acetaldehyde, not oxygen gas. So I'm gonna erase the oxygen gas for now. Alright. Now we're gonna have to try to calculate how many grams of acetic acid will be produced from this acetaldehyde. So the acetic acid CH3COOH that is going to be produced, we can use N, which is mole, equal to mass divided by molar mass. So mass gonna be equal to mole times molar mass, and we know that mole is 0.75 for acetic acid, and we're gonna have to try to find the molar mass. The molar mass of acetic acid going to be 12 plus 3 for hydrogen plus 12 for carbon plus 16 for oxygen plus 16 for oxygen and then plus 1 for hydrogen. It is going to be 60 grams per mole. So we have to multiply 60 grams per mole here. And that is going to give us 45 grams. And that is the answer. There is also another important concept that you need to know regarding chemical reactions and stoichiometry, and that is chemical yields. We will be looking at actual yield, theoretical yield, and percent yield. The actual yield is the amount of product that is actually obtained from a reaction. And the theoretical yield is the amount of the product that is obtained if all the limiting reagents react. And the percent yield is equal to actual yield divided by theoretical yield times 100. In a perfect circumstance, the actual yield may be equal to the theoretical yield, which gonna result in 100% yield. However, in reality, percent yield can be less than 100. Well, let's try a practice question to make this a little more clear. Under a certain condition, carbon monoxide gas reacts with hydrogen gas to form methanol. If the reaction is supplied with 210 grams of carbon monoxide and 28 grams of hydrogen gas, and 196 grams of methanol is actually produced, what is the percent yield of the methanol? Since we are dealing with chemical reaction, first we have to make sure that the chemical equation is balanced. On the left hand side we have carbon, hydrogen, and oxygen. And on the right hand side we also have carbon, hydrogen, and oxygen. On the left hand side, total carbon is 1, hydrogen is 4, oxygen is 1. On the right hand side, carbon is 1, hydrogen is 4, and oxygen is 1. Everything matches, so this is balanced. The next step is to try to determine the limiting reagent. And they give us 210 grams of carbon monoxide and 28 grams of hydrogen gas. Let's try taking a look first at carbon monoxide. So we have CO, which is going to be converted to mole, and they give us 210 grams, and that's gonna be divided by molar mass of carbon monoxide, which is 12 plus 16, and it's going to be 28 grams per mole. And that is going to multiply 1 mole of methanol can be obtained from 1 mole of carbon monoxide, and that is going to be 30, and that's going to be 4, and we're gonna get 7.5 mole of methanol if we use up the carbon monoxide. Now let's try to take a look at hydrogen gas. For hydrogen gas, we're gonna convert it to mole, and they give us 28 grams of hydrogen gas. It's gonna be divided by 2 gram per mole, which is the molar mass of hydrogen gas, and we know that 1 mole of methanol can be obtained from 2 mole of hydrogen gas, and that is going to give us 7 mole of methanol. So if hydrogen gas is used up, we're gonna get 7 mole of methanol, and this is the lower number. Hydrogen gas is the limiting reagent, and we're gonna be able to obtain 7 mole of methanol. So I'm gonna erase the carbon monoxide out for now, and then I'm gonna move up the hydrogen gas over there. The question here is pretty much give us the actual yield, which is 196 grams of methanol, and I'm going to write over here actual yield. But the question asks for percent yield of methanol. That means we need both actual yield and theoretical yield. So the next step is to calculate the theoretical yield of methanol, and that is going to be equal to 7 mole of methanol that we calculated earlier times 32 grams per mole, which is the molar mass of methanol, and that's gonna give us 224 grams of methanol. And the next and final step is to calculate the percent yield, and that is going to be equal to actual yield divided by theoretical yield times 100, and that is equal to 196 grams that is given earlier in the question divided by 224 grams that is calculated earlier times 100, and that gonna give us 87.5% of methanol, and that is the answer. So that is all for stoichiometry. All the 3 videos that I recorded should cover the key and common topics in stoichiometry. This is a fundamental and really important concept, so you might want to practice more when you get a chance. Good luck!